Thanks, everybody. I'm going to talk a bit about Bayesian statistical modeling, in particular some of the software that's out there that implements, sort of survey the landscape of software that implements this stuff. The nice thing is folks like Jake van der Plas, and I guess in my tutorial, for those of you who were there, we covered a lot of the groundwork of Bayes, and so I don't have to rehash a lot of this stuff. But Bayesian inference is all about calculating these posterior probabilities, and it's really nice because it's a really simple way to integrate our data to update our belief in the value of unknown quantities that we're interested in estimating. Why do we want to do this? Well, mainly because I come at it from a very pragmatic standpoint. I got into doing Bayesian inference because I was able to, using it, solve a lot of problems that I couldn't solve otherwise. And so the utility, aside from having sort of a philosophically satisfying approach to integrating data into our problem solving, it's a very useful way of going about statistical analysis. And the reason is because it's very, very simple, and you can build these use these simple building blocks together to model very complex things. So the main tool we end up using for this nowadays is something called Markov chain Monte Carlo, and MCMC is simply a way of sampling from unnormalized probability distributions, because it's very difficult to calculate that normalizing constant in the denominator there. And so rather than being able to analytically or even directly sample from these things, we have to come up with clever methods for getting at that posterior. And MCMC is, the only thing I'm going to say about it is it's simply a simulator for Markov chains, where the unique invariant limiting distribution of that Markov chain is some function of interest, and that function of interest is always our posterior distribution. And how do you get that kind of a Markov chain? Well, you build a Markov chain that satisfies this equation. It's called the detailed balance equation, where those probabilities of y given x and x given y are just essentially your sampler that's moving your point from place to place on the posterior distribution. And so there are a whole bunch of flavors of MCMC, and these are what I would call sort of the first generation MCMC algorithms, including things like Metropolis and Gibbs sampling and so on. And so what do we have? If we want to do MCMC, if we want to do Bayesian analysis for most problems, what have we got to deal with? Well, the granddaddy of them all is WinBugs, right? And we owe a big debt of gratitude to WinBugs, because before this we had nothing. We had hand-coded MCMC that had to be recoded every time you had a new problem to solve, and WinBugs had this really nice interface. It's like this big cockpit here where you can, push all the buttons you need and specify how much you want to sample and how much you want to burn and how much you want to thin, and you could even watch those red lines in real time sampling. It's pretty cool. All in this nice interface. And so the important thing is that non-statisticians could use this. But it has a number of drawbacks. Well, so this is what a bugs model looks like. It's this sort of domain-specific language that gets parsed and turned into a directed acyclic graph. But it looks very R-like, doesn't it? It's not quite R, but pretty close. Same assignment operators and such. It won't run in R, but you can interface with it a little bit. So the problems with WinBugs is first the win part of it, right? It's closed source. It doesn't compile on any other platform. You can't redistribute it or anything like that. It's impossible to debug. You'll get these trap errors that pop up after you've compiled it, and somebody might know what that, Andrew Thomas probably knows what that means, but I don't know what they mean. And so it's really hard to debug. So because it was closed source and folks weren't happy with that, they actually kind of froze WinBugs. There's no more development on WinBugs, and they spun off the source code into a project called OpenBugs, which is housed in Finland somewhere. And there are exactly 0.3 developers for OpenBugs. And the reason I know this is I asked Andrew Thomas, who's the lead developer, and I asked him how many developers there are, and he said 0.3, a third of him. So his kind of head and left arm works on OpenBugs now. And so, why not host it on, Git, open it up. His exact quote was, OpenBugs is only open source in the read-only sense, which is a little bit disturbing. So he's very protective of the source code. And the other problem is that the source code is Component Pascal. And I don't know if you're familiar with Component Pascal, but the more I read about it, the less I wanted to read about it. So even if it were open source, I don't think much can be done with it. So those OpenBugs and WinBugs, that's the de facto standard for doing Bayesian analysis. That's probably, my prior on that would be probably 70% of mainstream Bayesian work is done in one of those two programs. There's another package called JAGS that you may have heard of. I think you can get it on Homebrew, brew install JAGS. I think you can do that. JAGS you sort of think of as Bugs++, in that it's implemented in C++ rather than Component Pascal, which is super nice. Martin Plummer, who lives in France, he's pretty much the only developer. So we went from 0.3 developers to essentially 1. He expresses this as a platform for experimenting with ideas in Bayesian modeling. I really like that. It's definitely an improvement on WinBugs. It's sort of a variant of the Bugs language. You can sometimes run Bugs JAGS code unchanged in Bugs, but not quite. But it doesn't have a graphical front end, which is fine. It doesn't do any output processing. You rely on R to do that. It's cross-platform, and nominally it's extensible. And he really wanted people to write extensions, but I don't think people have. I've never seen a JAGS extension. SAS actually does Bayes now. Can you believe it? SAS. SAS has proc MCMC, which looks pretty cool. For those of you who like using SAS, but I don't think there are many SAS users at this conference, and I'm certainly not among them. But it's nice that they've finally come around to doing some Bayes. The other package that's sort of the first next generation package is something called STAN. STAN is not an acronym. It's named after this fellow, Stanislav Ulam, who's one of the fathers of Monte Carlo simulation and amateur Bud Abbott impersonator, it looks like. So they named it after him. This is the Gelman Lab out of Columbia University. Andrew Gelman's one of the top Bayesians around, and he hired a whole bunch of really clever folks to implement it. And so Stan is quite different from Bugs in the sense that it's statically typed and compiled. It's a lot of C++ code, a lot of very complex C++ code. BSD licensed, and it comes in a couple of flavors, basically interfaces to Stan. So you can run it from the command line, you can run it from R, Python, and MATLAB. And Stan kind of looks like this. It's kind of Bugs-like, but you see that it's got, you got to declare your types and so on, and declare your parameters. Not quite as accessible, I think, to non-statisticians as Bugs was, but it's there, and it runs more modern MCMC samplers that I'm going to talk about in a second. So that's, so we're going to talk about PyMC now, but really that is the landscape there. That's all. So this, considering how interested folks are in Bayesian analysis, there's shockingly little software support that allow people to do it. And so this is what motivated me partially to start PyMC. And also I didn't want to build my model in some domain-specific language that you have to interface with through little utilities that shuttle data to Bugs and shuttle results back. I want to write my model in Python. I want to be able to debug things and so on. And so that was kind of the motivation towards this. So PyMC, again, views the Bayesian model as this directed acyclic graph, and each of these components have different characteristics. Like this is a simple survival model where deaths are modeled as a function of a probability of survival, which may be modeled according to some covariates in a linear model, alpha and beta. And so some of these are unknown stochastic variables. Some are data. We observe how many things die and survive. And then there are some deterministic transformations of parameters. And so PyMC's got these objects that encapsulate those nodes and the connections between those nodes. So we can, express a variable as being exponentially distributed. So we get this exponential object here, and it's got a value, and it's got a log probability, which is used to do the MCMC. We can randomly sample from that, and you get a new value, and that new value's got its new log probability. So you got all these components. And then the nice thing about it is that you can specify your own. If you don't like our built-in distributions, here's a likelihood for a survival function for censored data, exponential parametric survival function. And all you have to do is write a Python function that returns a log probability, stick a decorator on it, stochastic, observed, deterministic, and you're rolling. So, and along with those objects, we've got objects that represent samplers and subclasses for doing particular types of sampling, like MCMC knows it needs to be sampling and tuning and things like that. It doesn't really know how to take an MCMC step, so we've got, it encapsulates a bunch of step methods. So some of our variables might use Metropolis, some might use discrete Metropolis because they're discrete variables and so on. And so you build it up from these components. You can swap them out with different versions, different subclasses of each other. So this is what a PyMC model would look like, right, for this survival model. So we got some priors up here, and here's our survival rates being calculated. This is just like a lambda function in Python. It's just a lambda object. And there's that survival function I showed you. So just a couple lines, you can write a nice little survival model. And generates a bunch of output for you. So these are posterior distributions of one of the beta parameters in that model. So it's quite nice. And it's been used a fair bit across, I sort of monitor, try to find out, occasionally put a call out on Twitter to see if anybody's used it for anything. And, we've got some astrophysics applications in here, lots of epidemiology like I do, community ecology, fire dynamics, that sort of thing. A particular application of mine, I do evidence-based medicine at Vanderbilt. You might wonder, evidence-based medicine, is there a different kind of medicine? Never mind. So in this case, what we're really talking about is doing systematic reviews. So this is a study of PKU, phenylketonuria, which is a very rare disease, so it's very understudied. A lot of underpowered clinical trials. Whenever a newborn is born in the hospital, they prick the foot of the newborn and they screen it for PKU. Basically, it's an inability for your body to metabolize phenylalanine, which is an amino acid, and that builds up in the bloodstream and it results in cognitive disorders, loss of IQ, and so forth. And so what we do in a meta-analysis for evidence-based medicine, you go in and you survey the literature and get all the studies that have been done on interventions for PKU and their effects on IQ, and put them together and model the studies as if they were data, essentially. And so you run into all sorts of problems with missing results and partially reported data and so on. And so we try to combine those and try to infer what the effect of different levels of PKU are on levels on IQ in these kids. And so we're able to take this directed acyclic graph that represents the model, and basically every node in that graph is a line in this code, and they're connected by the arguments. So one's the argument, the parents of one node are the arguments of its child. And so we're able to get really nice results like this. So this is a prediction. This is from the posterior predictive distribution. You can hand this to a doctor, right? Even a doctor could interpret this, right? And you can just read down what the level of phenylalanine is and what the probability of the IQ of that child dropping below 85 is for different situations of when PKU is measured and so on. So it's really, really good way of doing evidence-based medicine anyway. So that was PyMC 2, and that's sort of the kind of the release version right now. PyMC 3 is a complete rewrite. And part of the reason for the rewrite is we want to integrate some of the newer methods of MCMC sampling. And the primary developers on this are John Salvatier and Thomas Vicky. And what we're doing here is integrating something called Hamiltonian Monte Carlo. These are gradient-based methods that use essentially a physical analogy of a particle moving on a hypersurface. And so what we do is we add an auxiliary variable where we're essentially describing our posterior distribution as a Hamiltonian. So a Hamiltonian system, probably half of you are physicists, so I feel stupid trying to describe Hamiltonians to you, but you're breaking it down into potential energy and kinetic energy, where the posterior distribution is this kinetic energy, and or the potential energy, and the kinetic energy is an auxiliary variable, and the potential energy is just the log posterior, negative log posterior of that. And so we essentially simulate Hamiltonian dynamics. So the position on the distribution changes, so does the momentum. And what it involves are these sort of leapfrogging steps. So it takes, you think of it as a marble in a bowl, and you're kind of rolling that, you set that marble off, and it rolls to the other side, and that's another point, and rolls back, and so on. And so you take these little leapfrogging steps where you're simulating the changes in potential and kinetic energy. And so a Hamiltonian MC algorithm kind of goes like this. You sample this, a new velocity, so you kind of flick the ball in some random direction, and you perform n of these leapfrog steps, and then you do a Metropolis accept reject move, because it's not a perfect, you're discretizing the system, so there's going to be some error there. And so that's kind of what it looks like here, is that, it's kind of rolling along here, and then you see when it gets up to the top there, it starts rolling back, right? So you get to the other side of the bowl, it starts rolling back on you. And so, the comparison is this. So there's some Metropolis Hastings simulation going here, and it has a hard time initially. And this is just two autocorrelated normal distributions, and it kind of sits up in the upper corner. Doesn't mix terribly well. So it's not a very efficient approach, particularly when you have correlated variables. Hamiltonian Monte Carlo, on the other hand, does a really good job of spanning the support of that posterior distribution right away. So there's no burn-in. The acceptance rate is almost 100%. Problem with Hamiltonian MC is it requires a lot of tuning. So there's two parameters to tune. And so if it's too small, so that trajectory length is too small, it mixes really slow. If it's too large, you end up making lots of those U-turns. And then those leapfrog step sizes as well. You just trade off inefficiency and inaccuracy. And so there's a modification that Matt Hoffman came up with as a postdoc in Andrew Gelman's lab called NUTS. It's the no U-turn sampler, and as the name implies, it tries to avoid those U-turns up at the top. So it essentially tries to stop when it notices that the momentum is, when the trajectory is doubling back on itself. And it does this by building this balanced binary tree where these leaf nodes correspond to states of the system. And so it will take a step in one direction, flip a coin, take 2 steps in either that same direction or backwards, and then 4 steps and 8 steps until it starts to double back on itself, and then it stops. And so the difference is profound. So if you're doing, this is an example taken from Hoffman and Gelman's paper. This is a 200, a multivariate normal of size 200 with very high correlation between each of the elements. And you can see with Metropolis Hastings, it's not working very well. Down in the bottom corner here, these are independent samples, because we can independently sample from multivariate normals. And NUTS comes very close to independent. If you're going to use Metropolis or Gibbs for models this size, you're going to have a bad time. So what it required out of PyMC is being able to calculate gradients. If you look back to those Hamiltonian equations and so forth, you'll notice there were gradients in there. Gradients are hard to calculate generally just using pure Python, and so Theano very nicely does this for us. And so the biggest change is that PyMC is now backed by Theano rather than thousands of lines of Fortran code. So what we can do now, Hamiltonian Monte Carlo, NUTS is the big one, does slice sampling. You can now do a little bit of parallel chains, although very rudimentarily. Code base is totally simplified thanks to Theano. And what we have now are these really nice ways of doing regressions that is going to be really convenient for a lot of users because Thomas Vicky integrated PATSI into PyMC. And so this is a Bayesian logistic regression in like one line, right? So you import some data from pandas here, and this is just some height and weight relationships and predicting sex from height and weight. And there's our model. Male is a function of height and weight. Give it a binomial error, and you're laughing. Using nuts, no less, using the most modern samplers. So lots to do. None of us have any time to do any of this. We need to be able to deal with missing data a little bit better, some more automatic step selection like PIMC2 does. We really want to do some of this non-parametric Bayesian stuff like Gaussian processes and Dirichlet processes and other non-MCMC methods, approximate Bayesian computing and those sorts of things. And the documentation is way behind, as these things tend to be. So, you know, we have a chance here to really, I'd like PIMC to be that place where you can experiment with Bayesian models. And as I think I showed, you know, it's sort of ripe for the taking in the sense that it's an underserved community, and I think Python's a really good place to do Bayesian computing. And so, you know, if any of you are Bayesians or want to know more about it or are interested in implementing these models, particularly if you're better Python coder than I am, which is probably most of you, I encourage you to have a look at the PIMC code and get in touch with us and you know, and contribute where you can. So that's it. I probably don't have time for any of these questions, but thanks for your attention.